Hello everyone, welcome to my channel Maths Learning Online. I'm starting this channel keeping in mind CBSE 12th board exam 2018. I will upload all types of questions chapter wise that should be practiced before board exams. Apart from NCERT, these questions are going to help you getting good marks in your maths exams. I have constantly practiced these questions with my students and they showed remarkable improvement in their maths skills. I just want to share these questions with all the students, those who are appearing in boards this year. So practice this and definitely you're going to get good result and your marks will definitely going to improve. Now, as we are going to learn step by step, chapter by chapter, I'm going to upload several questions which are important. They will be like from NCERT also, which came in last 3 years, like 2015, 16, 17. I have taken 3 years, last 3 years papers, questions also in these question banks and like worksheets. So you can be aware of the pattern that these board people are going to set and what type of questions generally asked in the exam paper. You might have also seen the last year's paper and you might be having a general idea about it. So these are the important questions which I can guarantee if you do it well, then you are going to score very good marks in your exams. So now let us start with relations and functions and improve our by this time I'm sure that you all are familiar with the concept and revision might have been done once. So I'm directly discussing the question. I'm not discussing any concept with you all. Conceptual phase is over, and by this time in all the schools the conceptual part is almost done. Tests are going on or exams are going on for the revision of the concepts. So I'm directly uploading the questions. If there is any problem in concept or something also, you can ask me in my comment box. So the first chapter, relation and functions here, and the first question, check whether the relation on R defined in the set 1 2 3 4 5 6 as R equals to AB such that B equals to A plus 1 is reflexive, symmetric or transitive. Okay, now this relation can be written as as you can see here, that here R is AB such that B equals to A plus 1. Now in place of B, if I write A plus 1, that will be okay, right? Now this A and B both should belong to this set. Now A and A plus 1 should belong to 1 2 3 4 5 6. Now if the value of A is 1, so what will be the value of A plus 1? It will be 2. If the value of A is 2, then next this will be 3. If the value of A is 3, B is 4, A is 4, B is 5, A is 5, B is 6. A cannot be 6 because there is no 7 here, where you have to make sure that B also belongs to this set, right? Now 7 is not there, so we cannot take A as 6. Now R is not reflexive as AA does not belong to R. AA means the identity element, like 1 1, 2 2, 3 3 does not belong to this relation. It is clearly seen, right? Now secondly, also R is not symmetric as AB belongs to R but PA does not belong to R. And you see AB is there, like 1 2 is there but 2 1 is not there. Now again, R is not transitive as AB belongs to R and BC belongs to R. Now this implies that B is A plus 1 and this implies that C is B plus 1. The difference between A and B is 1 and the difference between B and C should also be 1. Now here what happens, C is B plus 1 and B is A plus 1. So in place of B, if we write A plus 1 here, so it will give you A plus 2. So there will be a difference of 2, not A plus 1, right? So definitely this AC does not belongs to R. Now if we take the example also, 1 2 belongs to R, 2 3 belongs to R, but 1 3 is nowhere to be seen. Can you see it? Because in 1 3 there will be a difference of 2, not 1. Are you getting it? And now we have only the second element is 1 more than the first element, and 1 3 may the second element will be 2 more than the first element, so that will not fit in this relation. So that relation is not going to be counted. Okay, so this relation is neither reflexive, symmetric, or transitive. Okay, now question number 2 here in this chapter. This is very good question which I came across and I thought you should know. This is, if R is an equivalence relation on set A, then show that the inverse relation R inverse on A is also an equivalence relation. Now this is the type of question which can be rephrased in different way as well. Now this can be rephrased as, the inverse of an equivalence relation is an equivalence relation, right? Can you see it? The inverse of equivalence relation R is also an equivalence relation, right? So they have not given you in terms of R or set A, or nothing is mentioned here in this phrasing. So the inverse of an equivalence relation is an equivalence relation. Now let us just start with this. Since R is a relation on A, R is a subset of A cross A, or the number of elements in R can be equal to the number of elements in A cross A. So either it is a subset or equal. So we can say that R is a relation on A. Then R inverse will, what is R inverse? For example, if AB belongs to R, then BA belongs to R inverse. So remember this, okay? So R inverse is also a subset of A cross A or equals to A cross A, because the number of elements in R will be same number of elements in R inverse. Number of elements in both of the sets will be same, only their order will be changed, right? So here R inverse is also a relation on A. Now we have to check it reflexivity, symmetric, and transitivity. Now let A belongs to A, then AA belongs to R. Since R is already equivalence relation, so it will be reflexive. Now R inverse will be, if you interchange these two, this will also be AA. So AA belongs to R inverse as well. For all, this symbol is for all A belongs to A. So R inverse is reflexive. Now symmetric. If AB belongs to R inverse, symmetric में what we should do that, if AB belongs to R inverse, then BA should also belongs to R inverse, then only R inverse will be symmetric, right? Now let us say, let AB belongs to R inverse, so R will be the conversion of these, interchange of these elements. BA will belong to R, and R is already symmetric, so AB also belongs to R. When AB belongs to R, so BA belongs to R inverse, right? So from here we arrived to this conclusion. Are you getting it? So AB belongs to R inverse and BA belongs to R inverse for all A belongs to A, so R inverse is symmetric. Now come to transitivity. Let AB belongs to R inverse and BC belongs to R inverse. Then BA belongs to R, interchange this. BA belongs to R, CB belongs to R. Now since R is transitive, so CB, BA, they both belong to R. Third element should be CA. So CA belongs to R. Now the inverse of this will be AC, right? Now from here, AB belongs to R, BC belongs to R, AC belongs to R. So this means what? That AB belongs to R inverse, BC belongs to R inverse, implies that AC also belongs to R inverse for all value of A belongs to A. So R inverse is transitive on A. Hence R inverse is an equivalence relation on A. Now next sum here, question number 3. If R and S are two equivalence relation on a set A, then R intersection S is also an equivalence relation on A. Now, this sum can also be phrased in another way, that is, the intersection of two equivalence relations on a set is an equivalence relation on a set, right? Now, two equivalence relation has been described to R and S, and on a set, which set we are talking about? We are talking about set A, right? Now, in this, again, as we have done in the previous sum, R is a subset of A cross A or equals to, then S is a subset of A cross A or equals to, so intersection, their intersection will also be from A cross A. So R intersection S is also a relation on A, right? Now we shall show that it is an equivalence relation on A. Let A belongs to A, then A belongs to us. Since R is already equivalence relation, S is already equivalence relation, so identity element belongs to them, like symmetric, reflexive. One AA belongs to R and AA belongs to S. So AA belongs to R intersection S for all A belongs to S. So R intersection S is reflexive relation. Now for symmetric, if AB belongs to A such that AB belongs to R intersection S. Now since AB belongs to this, so AB belongs to R and AB belongs to S separately. Then only, since it is intersection, only the common element belong to both of these, right? So AB belongs to R and AB belongs to S. Now since R is symmetric, S is also symmetric, AB ka BA belongs to R and BA belongs to S. So BA belongs to R. Both the elements belong to R and S, so we can write this the same element belong to two different sets. So we can say that the intersection of these two sets is this element. So that will be B comma A belongs to R intersection S. Now AB belongs to R intersection S, BA belongs to R intersection S. For all AB belongs to R intersection S. Thus R intersection S is symmetric on A. Right? I hope you understood, and if there is any problem or any thing you haven't understood, you can ask me in my comment box. I am definitely going to give answer to that. Now transitivity for this, let ABC belongs to A such that AB belongs to R intersection S and BC belongs to R intersection S. Now this element also belongs to R intersection S and this element also belongs to R intersection S. It means this element belongs to R and S separately. Similarly, BC belongs to R and S separately. So we are going to put them in two different brackets. That AB belongs to R, AB belongs to S. Right? Then BC belongs to R and BC belongs to S. Now AB belongs to R, what we are going to do? We are going to group the elements of R and the elements of S. AB belongs to R here, BC belongs to R here, and AB belongs to S here and BC belongs to S here, right? Now AB belongs to R, BC belongs to R. So since R is transitive in itself, the AC will definitely going to belong to R. Similarly, AB belongs to R, S, BC belongs to S, so AC belongs to S since S is already transitive relation. Therefore, this one element AC belongs to R and S, two different sets, two different relations, right? So we can say AC belongs to R intersection S. So R intersection S is transitive on A. So we can say since R intersection S is reflexive, symmetric and transitive, it is an equivalence relation, right? So the intersection of these two, R and S, the intersection of R and S is an equivalence relation on the set, right? Now let us see the next question. Question number 4. Show that the relation R on the set n cross n defined by ABRCD. Now see the pattern. AB is one element of this relation, CD is another element of this relation, and they are related. These two elements are related in a way that A plus D equals to B plus C, right? For all A, B, C, D belongs to n cross n is an equivalence relation. Now what happens here basically? Here, in this question number 4, let AB belongs to n cross n, right? In the form, since AB belongs to n cross n, implies that AB belongs to n. Now A plus B equals to B plus A, since addition is commutative on natural numbers. AB relation AB. So if we add, we can write this as AB plus AB. So A plus B and B plus A will give you the same answer. So we can say same element is the relation with the same element for all AB belongs to n cross n. So R is reflexive, right? Because we can write this B plus A as A plus B also, and then A plus D and C plus B plus C. The same pattern which we have seen in the question, right? Here is the question. You can see it clearly. The pattern here, A plus D equals to B plus C, right? Now, here we have to show the symmetry of this relation. AB CD belongs to n cross n such that AB R CD, AB with relation to CD, then if AB and C, if this is a relation with this, then this should be a relation with this. Yani ki what we have to prove, CD is in relation with AB. Then only we can prove that this is symmetric. Now we can write it in the way this relation has been defined, that is A plus D equals to B plus C, right? Now we can write this here and this here. C plus B equals to A plus D. This we can write like B plus C, we can write C plus D because it is commutative and we are talking about the natural numbers here, right? Now this can be written as CD in relation BA or AB. Are you getting it? Because AB and BA, they both are in addition of natural numbers, they are commutative, so we can write it in any order. Thus AB belongs to CD. Here AB R CD implies that CD R AB. So it is symmetric for all values of AB CD belongs to n cross n. So we have done what? Transitive, reflexive, symmetric, now transitive. Now, for the transitivity of this question, what we are going to do, we are going to take 3 elements, because we need 3 elements here. AB relation CD can be written A plus D equals to B plus C. Then CD relation EF can be written C plus F equals to D plus E. Now adding these two, we can see D and C can be cancelled out, right? Left side of this and right side of this. So AF equals to BE, or we can write AF equals to E plus B, which can be written as AB relation EF, right? Thus AB relation CD and CD relation EF implies that AB relation EF from here. Are you getting it? For all value of AB, CD, EF belongs to n cross n. So R is transitive relation on n cross n. Hence, we can say since R is reflexive, symmetric and transitive, so R is an equivalence relation.